so we started recording. Okay, so welcome to the third lecture. We're going to keep talking about compute models today. So we're going to finish that off today. And then next week, we're going to continue on this kind of overview of why would you use an FPGA, and by looking at FPGAs versus other devices. So Lab 1's been released. Hopefully everybody's gone and taken a look at that. It's partly a tutorial on how to use CAD tools. So Quartus and ModelSim, which are, well, Quartus is for Intel FPGAs, but other vendors have similar CAD tools to implement a design, and then ModelSim is the most popular simulator to verify your design. So part of this purpose of this lab is to learn those CAD tools if you don't know them, to learn them better from an optimization point of view if you have used them but haven't used them in that much depth, and to look at a couple of the computational models that we've studied and optimizations like pipelining that we've looked at and see how they work on a relatively simple computation circuit. And then you'll go further in optimization on Lab 2 where the design will be a bit more complicated. Let's see, so as usual, there are readings, so you can submit questionnaires on these. For next week, there are two. One is basically a comparison of software versus hardware. So how efficient is a processor versus direct hardware execution? So that kind of fits into the theme of next week, where we're looking at how efficient are FPGAs for different kinds of computations. Part of the answer to that is, well, how efficient are CPUs? Because they're the other programmable platform that you're often going to be considering. Another part of the answer is how efficient is an FPGA versus fixed hardware, like an ASIC. And the second paper listed here gives some insight into that. That's a difficult question to answer perfectly. It's different for every design. But the second paper looks at, if we have a relatively simple model of computation, we can use all the resources pretty well. How much computation can we get done with things like CPUs, GPUs, DSPs, and FPGAs? So it's kind of a peak performance analysis. Like, you will not exceed this performance. And if we look at those numbers, how do they vary across different kinds of devices? So those two papers give some background in terms of helping you select for a certain kind of computation, should you use an FPGA or not, and how efficient do you expect it to be. And we'll talk about that more next week. Sorry, I have two computers set up, so sometimes I forget which computer is doing what. So a few students have asked me for references on Verilog. Lab 1 is most easily written in Verilog or System Verilog. It technically can be written in VHDL as well, but you'll have to link your VHDL code to the system, to the Verilog test bench that we gave you, which is doable, but a little more complicated. So it's easiest to write it in Verilog or System Verilog. Those are also the most popular HDL in North America. So if you don't know Verilog, how can you learn it? There are lots of different resources. So you can go buy many different textbooks. You can look at many different web resources. A few pointers. For University of Toronto undergraduate students, we use Brown and Vradezik, so both professors at U of T, but this is a very popular textbook that's used a lot around the world. So you want to get the Verilog version. They have a VHDL version as well, but Verilog is probably the better language to learn these days. System Verilog is really the next generation of Verilog. So they give it a new name, but it basically just adds some additional features to Verilog. System Verilog has a lot of features for simulation. So those are basically for writing test benches. For both Lab 1 and Lab 2, we wrote the test benches for you, so you don't have to write them. So the part you care about is what's called the synthesizable subset. So the part of the language that actually describes hardware that a tool like Quartus, or if you're using Xilinx Movado, can actually turn into hardware. So most of the language will not turn into hardware. It's just about providing stimulus to something you're testing. We only care about the synthesizable subset because you want to actually be able to make hardware. System Verilog has a few features that are nicer than the older Verilog in terms of how you describe hardware. So again, there are many resources online. The link I've put there if you just change the number 1 to 2, 3, and 4, you'll go through the first 4 lectures of this professor at UCSD. I think these lecture notes are a pretty concise overview of how to use System Verilog to describe hardware. So if you don't know it, you can go take a look at that. If you know HDL and you're looking for more advanced references, this link to Sutherland is basically 2 things. You can buy his textbook, which is about how to use System Verilog for design. So again, making hardware, not about writing test benches to simulate it. And he has free papers as well on his website. So he's written a bunch of papers on how can you best use Verilog and System Verilog, what are some gotchas, what are good coding styles, and so on. So if you want to learn how to write better System Verilog, you can go look at those papers. And the last link is similar. So this is Cliff Cummings, who is a well-known Verilog trainer. And again, he has a bunch of links to his papers on his website that go through relatively advanced language features, gotchas, coding style suggestions. So you don't have to go through these, but if you're kind of looking for guidance on how might you code better, you can go take a look at them. If you're just learning the basics of the language, then I'd start with the top 2 for sure. Let's see. So I'm going to switch to the tablet view and write some notes. We're not going to use PowerPoint very much for this lecture or for the first few lectures. Later on, we'll use more PowerPoint. Any questions about Lab 1? Or is it all pretty clear, or perhaps not many people have started on it? Okay, so if it's all silence, I'm going to take that as it's all going well so far. I saw some discussion on Piazza, which makes me happy because it means that at least some people have started on it. I've posted my handwritten notes for this lecture and the slides. So if it's easier, you can follow along with those. Don't feel like you have to transcribe things down. Okay, so we've been talking about how do we organize computation in FPGA, because we can kind of do anything we want in this chip. And we talked a bunch about streaming. So streaming data path, very efficient way to capture computation. And we talked about some optimizations we could use with streaming data path. But we're now done with that. We're now going to move on to other ways we can organize computation. Okay, so from quite inflexible to gradually more and more flexible versions. Now we're into something that's not a streaming data path design. And it's finite state machine with a data path. So that's what SFMD means. Okay, so what is this? So this is like, it's kind of like a processor, but it's not a microprocessor. Okay, so what do I mean by that? Well, like a microprocessor, it's got a reusable data path. So let's say that I have computations that I need both multiply and I need add. Okay, so I build a multiplier and I build an adder in my hardware. But I want to reuse them. I'm going to do more complicated computations by building up results a little bit at a time, essentially in temporary registers, so much like a processor. Okay, so how am I going to do that? So I need to finish my data path. I've got a multiplier, I've got an adder. I need to choose what goes into these things. So I'm going to make some multiplexer that's going to allow me to choose what goes in. And let's say I've looked at my computation and I've worked out that I sometimes need to bring an input in from elsewhere, maybe the outside world, maybe some other module in my design. So I have a couple inputs, in 1 and in 2, that could come from somewhere else in the design. I'm going to need a control signal to control these things. But to compute more complicated things, that's not the only input I can send into my multiplier and adder. Okay, so these multiplier and adder each have an output, and I'm going to actually multiplex between those two, and I'm going to send them to registers. Okay, so this actually I'm going to represent not just one register, but basically a bunch of registers. So that's what this is. This is a bank of registers, basically. Okay, so far I can do multiplication, I can do addition, I can choose where to write, I can store the result in some temporary registers. To build up more complicated computations, I want to be able to feed the output, so my temporary results, back in to my adder or multiplier. Okay, so I'm going to add some wiring to do that. And now I've got a data path that kind of looks a lot like what you build in a simple microprocessor. I've got a multiplier, I've got an adder, I've got a temporary register file, and I've got some muxing. And now I need to control this. So in a microprocessor, I would control that with my decoded instruction stream, but I know that I don't need something that general. Okay, so I've built hardware that I know is going to do relatively repetitive calculations. So I'm not going to control it with an instruction stream because that would take more area than I want. So I still need to bring out some control signals. But what I'm going to use to control those control signals is a finite state machine. Okay, so my finite state machine is going to choose what each of these muxes is selecting. It's going to choose which one of these registers is active for both read and for write. And that's going to let me basically do anything I want that consists only of multiply and addition, and where I don't need more temporary values than I built here. Okay, so what's this suitable for? So if you're designing a system, when would you use this instead of using some kind of streaming hardware? So let's say that you're actually going to build this for Lab 1. So you're going to build a shared operator design, which is basically this. It's a finite state machine controlling a data path. So we built here just two operators. We can do multiply, we can do add, and we can control them with a finite state machine, and we can store some temporaries. So when does this make sense to do instead of doing a streaming data path? Let's say we're doing Lab 1. Lab 1, we're calculating a Taylor series expansion. So we actually don't want to do just one multiply add. We actually have to do about, for every computation, we have to do about 6 multiplies and additions. So when does this make sense instead of doing it streaming hardware? Streaming hardware, I would just make 6 multipliers, 6 adders, and it would compute everything I need spatially. This is not computing it spatially. It's computing it more sequentially. So when should I use this? Someone has to have an answer. Oh, okay. Actually, sorry, this is my fault. I've forgotten where my chat window was. Okay, so I was waiting for a verbal answer and forgot. Okay, so the operation takes too much space. The operation is quite repeated. Control flow, low hardware resources. Algorithm has lots of branches. We're using the same hardware. Yeah, so lots of good ideas here. So one theme here is when you want to save area. Okay, so if you're running out of space, maybe the spatial hardware version is too big. That's definitely a good reason. This is small. As long as my finite state machine doesn't get too complicated, which usually it doesn't. So if I was doing an incredibly complicated calculation, maybe that FSM gets complicated, but usually it's pretty small, and this would be pretty small. So that's a good reason. Another reason that people are highlighting is, well, maybe I just don't need that much performance area. I don't need the performance of a streaming hardware implementation, so why bother? So area savings, particularly when I don't need all the performance. Other points people are pointing out, yeah, basically things that make a processor good. If there was also lots of control flow, like if my decisions were dependent, I needed to look at the previous output to decide what to do with the next one, then this architecture also is a reasonable choice. Because it does things serially, it's pretty good at control flow, where spatial hardware can do control flow, but it gets relatively inefficient. You basically compute everything and then use muxes to select which result you're going to take. So a lot of your hardware kind of is computing things that you'll throw away. So yeah, these are all good ideas. So it's suitable for rare or not highly parallel operations. So if you just don't need the speed, don't don't waste the area. It basically saves area versus streaming. So another case where you use it is just where the streaming is just too big. It's not even an option because it won't fit. Okay, and hopefully people can see how this is a lot like a processor, but I've done hardwired control instead of using an instruction stream over here. Whoops, let me get rid of that. All right, I won't use that option again. Okay, so let's look at things that are kind of related to that. Another thing you can do is VLIW. Does anybody know what VLIW is? I'm sure some people do. So you can just type it in the chat, or if you're really brave, you can unmute yourself and actually say it verbally. So maybe an unusual thing this semester, but yeah, so very long instruction word. Okay, so very long instruction word, basically this means I'm going to control a data path with instructions. Okay, so the term comes from processors, where you have, instead of a 32-bit instruction that can specify, maybe 1 or 2 operations, you have a longer instruction word that can specify more operations. So it's a technique that processors use to expose more parallelism, because they can encode more in the instruction word. We can use it when we're designing hardware, though, too. So it's a lot like our finite state machine with data, but basically it may be easier than making an FSM for basically complicated data paths. If you have a lot of function units, you might, and you have a pretty complicated control flow, you might find the FSM starts to get complex and maybe more complex than you want, in which case you can basically have instructions that you sequence through. So you make a very simple processor from a control flow point of view, and it controls a whole bunch of functional units. Okay, so for some data paths, this might be easier than an FSM. Okay, so another thing that's you may have heard of from the processor world is Simdi. So what does Simdi stand for? I'm sure somebody knows this. So if you know it, you can, again, type it in the chat.
Single instruction multi-data.
Yes. So thank you, Edwin. So so single instruction, multiple data. So it's kind of like VLIW, but what it means is you've got many parallel execution units. But they're all the same. In VLIW, you can have many different execution units, but they can all be different. Every one of them has got its own piece of the instruction word controlling it. In Simdi, they're all the same. Okay, so why is this a useful thing? Well, it can make your hardware more efficient because you can share the control. Control is just kind of overhead when you're doing a computation. Your data path is actually doing the actual computation you care about. The finite state machines and these instruction sequencing that I'm talking about is basically overhead. So if I can organize my data path so that I have a whole bunch of execution units that all use the same instruction, I can share control, and that could be an instruction stream, or it could be in a finite state machine. So we can have a finite state machine that's producing control signals and just have those broadcast to a bunch of execution units. So it's smaller, right? We're going to save area by doing that. So what does it look like? So I've got a control unit, could be instructions, could be an FSM, and that is going to control a whole bunch of different things. Function units. So a whole bunch of identical function units are being controlled. Maybe they're being fed by some on-chip memory. So I have identical memory units. And all those memory units are also getting the same control. Okay, so it's an efficiency technique. It also can help you think about a computation. So it can be easier to think about, I've got one state, but that state's controlling a whole bunch of function units that are all operating in lockstep, than some other styles like VLIW, where maybe you have a whole bunch of unrelated things going on. So it can be easier to, or it's more efficient for your control to do it this way. It also can be easier to think about, depending on what you're trying to do. I'll probably show you a little more about this in a lecture or two, but I had a previous grad student who was doing a matrix solver. So he's taking very large matrices, so many rows, many columns, and he's basically trying to factor them into a lower triangular and upper triangular matrix. And that fit very naturally to do the same operation on every element in a piece of a row. So you could have many function units all operating on different columns, basically, and the instruction, one instruction or one control unit can control them. So his control unit was a finite state machine, but it controlled a whole bunch of different functional units. So that was an LU decomposition engine, right? So it's working on a big matrix. So many values in this matrix. And basically, he could fill, the biggest chip he could get. So at the time he did this, the largest chip he could get, it's a Stratix 4 chip. He could build 144 processing elements in it, and they were all operating in lockstep. So that amortized the cost of his control. He only needs one control unit, and it made it easier for him to think about, right? So, whoops. Because every PE was basically taking, the control unit would go through row by row, but as it went through rows, every PE was taking a different column, but doing the same thing. So it's taking values from this row and adding them to the row below, and every PE got the same instruction, grab the value in this row and subtract it from the value in this row, and they're all just working on different data, but they're all doing the same operation. Easier for the student who do this to think about it as well, because he doesn't have, well, everybody's doing everything in lockstep. It's easier to organize. Okay.
There's a question in the chat window.
So is GPU a Simdi? It's very close to Simdi. We'll talk a bit about GPUs in a week. So GPU is technically called single instruction multiple thread. So that's what usually they call GPUs. It's very close to Simdi, but it's a little more flexible than Simdi. You can actually, in some cases, can have slightly different instructions operating on the data, but it's fairly accurate to think of it as Simdi. So, Andrew, I don't know if you would add anything to that or not. Can you give a precise answer or a succinct answer of what's the difference between single instruction multiple thread and single instruction multiple data?
So I think the SIMD, I'm trying to find the best way of describing that difference. Yeah, I don't know.
They're very.
I don't know if I have a clear way of differentiating
I don't think
between
I have a
them.
very good way to answer it either. It is mostly Simdi, right? And this is one of those things where it's possible even the new term may not be entirely justified. There are a few differences, but it also can sound cool to make a new term. It's mostly the same data. They do have a few enhancements, so that in some cases you can do simple if conditions and so on. So even though you're doing a slightly different operation, you can handle it.
I guess the main difference might be that they might be operating on the same data. So it's not necessarily multiple data, right? And there are also all the synchronization and fencing fancy stuff.
Yeah, that's kind of where they don't get their performance, though. Do you know what I mean? They get their performance when all of the little functional units basically are all working on their own data. When they have to synchronize, they can do that because often you need to synchronize at certain points, but that's where they actually lose performance. Do you know what I mean?
Yeah,
So,
but I guess this is where they gain more flexibility compared to the SIMD.
true. Okay, so they don't always have to do it as Simdi. So,
Yeah.
so that's a good question. And I don't know if we gave you an entirely satisfied with a little bit more flexibility. Let's see. I see there's another question. How is that different from a mesh of CAs? CA is, what's a CA? Cellular Autonoma? Is that what that is?
So this was regarding the example that you just gave. That's
Okay.
the matrix reduction.
Yeah. How is it different from a mesh of CAs? I guess the data flow is different in this case. So I haven't, these matrices are big, so they don't actually fit on chip. So the matrix engine is actually taking a piece of the matrix that is stuck in memory. Technically, it's got 3 different pieces, but it's working with pieces of the matrix that are on memory. And those pieces are still relatively big. Those are called blocks. So 144 columns by typically maybe 100 rows or so. And it actually has to do a bunch of operations. It has essentially n cubed compute. So it basically has a lot of compute to do. Those compute steps that it has to do always do the same thing to every element in a column. But if you tried to do it with a cellular autonoma, it basically wouldn't work that well. You sometimes are taking this row, and I'm highlighting here, and you're subtracting a scaled version of it from every element in this row, okay? And then you do it with the row below as well. So it's not always nearest neighbor computation. It can always be organized in lockstep, where you're doing the same thing to everybody in a column, but you're operating sometimes on different, which row you're working with or which pairs of rows you're working with is changing over time. So having a finite state machine organize that is useful.
Okay, got it.
Okay, so that's a good question. Okay, so H, so soft processors. Okay, so who knows what I mean by a soft processor? I'm sure lots of people do, but maybe not everybody does. So who's heard of a soft processor? What does this mean? So you probably inferred a bit from the 2 words. Any thoughts? Okay, so what is a soft processor? Okay, so it's a processor. What does the soft mean?
It's a processor that can be configured onto the FPGA.
Yeah, so it's a processor that we build. We don't go buy an Intel processor or an ARM processor that's actually been built out of transistors. We're actually going to build the processor out of the reconfigurable resources of the FPGA. So out of lookup tables and block RAMs and programmable routing and so on. Okay, so why would we do that? Because there is a cost to programmability. We're going to see this next week, but basically there's actually a significant cost to the instruction style programmability of a processor. There's also a significant cost to the rewiring style of programmability of an FPGA. So when we actually have a soft processor, we kind of get both. We pay for the overhead of building everything out of these reconfigurable resources, and then we pay for the overhead of the fact that a processor is really an interpreter. You know, it takes an instruction and it looks at it to see, what do I do? And then it gets the next instruction, looks at it to see, what do I do? Whereas just direct hardware execution just does things. So we've got 2 levels of programmability, which is going to cost us efficiency. So given that, I just kind of told you what the cost of this is. Like, what do you think it's good for? What? Why would I use this? Should I use this for my main computation? Okay, so I see some various thoughts on this. So yeah, so the basic place where this makes sense, in my opinion, so there are other people who have different opinions, is this, it's basically useful for housekeeping. It's basically useful for things where you don't need that much performance. So where would that be? So useful for housekeeping. FPGAs enable very large hardware systems nowadays. So there may be some setup, some initialization, and putting that all in a big finite state machine can be a pain. Or there may be some error conditions that are rare, etc. Things where you don't care that much about performance, but the logic's relatively complicated. So you can use a soft processor for those. You can use them for hardware control. Okay, so we just talked about how we can build hardware engines where they're single instruction, multiple data. So a lot of functional units. Well, we could provide the control for those functional units, not from a finite state machine. We could actually use a soft processor. And because most of our logic is going to be in these many functional units, the fact that the soft processor is not that efficient is kind of amortized away. It's still not that big. It's just doing control. It's okay. Let's see. Where we probably don't want to use it, we probably don't want to use it for not for the heavy lifting, okay, where we're basically doing most of our computation, okay? And the reason is there's 2 levels of programmability. Okay, so I should have put this in as a poll, but didn't think of it. You can type thoughts in the chat. What do you think the cost of a level of programmability? So we've got 2 different levels here, right? Instructions is the way processors gain programmability. And we have reconfiguring wires and truth tables and so on, which is where the FPGA gains programmability. Roughly versus building just dedicated hardware that does exactly one thing. So very inflexible, very risky to build hardware that does exactly one thing, but also very efficient. How much cost in terms of area delay product, which means how much less throughput do we get from a unit of silicon, do you think each of these levels of programmability costs us? Okay, so I'm not looking for a very precise answer because this is not a very precise question. There's no one answer. It depends on your computation. So, but is this like a 50% penalty? Is it a 2x penalty? Is it a 10x penalty? Is it a 100x penalty? Like what kind of number are we looking at? So I see a couple of people have already guessed like 10x, and Marius has guessed 100x. Yet the number is pretty big. So the number it's a big loss. So it's about 10x. It can be 100x, and it's typically at least 10x. Okay, so it's bigger than you might think. There's a big cost to programmability. So that's for each level. And we're going to go through a couple of papers. Well, you see one of them that you're going to look at next week, which is doing computations on a processor versus hardware. And we're also going to look at another paper that tries to compare FPGAs to ASICs. So we're going to try to quantify these numbers. But 10x is a pretty reasonable ballpark number. And in some cases, it could approach 100x for each one of these levels. So we're paying a pretty big cost. I see there's another comment in the chat from Camilo about another interesting question, which is most FPGAs now include hard processors, at least most of the big ones. So not all. Some FPGAs don't have hard processors, and most small FPGAs don't, but most big ones have them. Okay, so why do soft processors still exist? Okay, so why not always hard processor? Okay, so basically often these are on the same chip. Okay, so I should clarify what I mean by a hard processor. A hard processor is just, it's a conventional processor. It's built out of transistors and wires. It doesn't have, reconfigurable wiring. It doesn't have, it's not built out of lookup tables and so on. And as I said, most large FPGAs now have typically 2 to 4 processor cores, along with a cache and a few peripherals. So why don't we always use those? Okay, and yeah, I see some good answers. So basically, First, you should use them if they fit well. So if you need a reasonably high performance processor, they're a good choice. So there's no reason not to use it. You should just use it if it's on the chip. But there are a few reasons. So one is the cost of communication. It might be pretty far from your hardware units. Those 4 cores, usually there's 4 ARM cores on a modern high-end FPGA. They're kind of on one, at the very top of the chip or on one side of the chip. So they might be pretty far from your hardware units. You might need many stages of pipelining and a lot of wiring to get that processor to control your functional units. So it may be in an inconvenient location. It may take you quite a few cycles to get to it. And because of that, you might be better off just building a soft processor right where you need it. Another one, which is kind of related, is basically, so coprocessor. So you could use that hard processor to control hardware units, but it's not that flexible. So depending on how many processors you need to control your hardware units, maybe you need 10 different processors in 10 different parts of the chip to control different hardware units. You can for sure do that with soft processors. You've got one hard processor subsystem. So, you know, it might not be the most convenient. It might take too many clock cycles for the data from the processor to get there. You may not have exactly the wires you'd like coming out of it. You may not have enough of them. So when you're controlling hardware units, that's another reason. And yeah, it can run out of them. Okay, so usually only 4. And some FPGAs don't have them. So maybe that's not the best reason, but you do use soft processors when they're your only choice. So yeah, I don't believe that using lots of soft processors for the heavy lifting makes that much sense. But it is interesting. There are, you know, there've been papers published for people who have put, you know, 1,000 soft processors in an FPGA by making them, you know, quite limited in their functionality. So they can strip out everything they don't need for their computation, trying to make them smaller, and then they can fit a lot of them in and split the computation across them. And so sometimes you can get reasonable performance from that. So I don't think it makes that much sense to do your really heavy lifting on a large number of soft processors, but I do have to point out, if people modify the soft processor enough, they pull enough unused circuitry out of it, they customize it enough, then it can become useful for the harder your computation. But it probably isn't the smartest thing to do with kind of an unmodified soft processor that, you know, is like a RISC-V soft processor that's pretty similar to what you could get in a hard processor subsystem or go by. Let's see. Okay, so let's keep on with processors. So type I is augmented processors. Okay, so this kind of goes into the last reason that people, well, one of the main reasons people talked about using soft processors is we can control hardware with them. We can integrate them pretty closely with a coprocessor. And in some cases, that's easier to do with a soft processor where we have control than a hard processor that might be far away and we can't change it at all. Okay, so there are a couple of ways that people augment processors. Okay, again, typically soft processors, because it's hard to augment hard processors. You can't really change. So you can augment a hard processor if you're in Intel's CPU design division, maybe Apple's CPU design division. But if you're not in one of those, you're not augmenting a hard processor. So, but everybody can augment a soft processor. Okay, so anybody know any ways that we can augment a processor? So make it more efficient for certain computations. I guess I told you one way, which I'm not going to talk about more, and we can make it more efficient. That's actually a subtractive one. Take everything out that it doesn't need. Okay, so you can make a very, sorry about that. You can make a very stripped down processor. But I'm not going to talk about that further. What are ways that we can make a processor faster for certain computations? Expand, okay, yeah. So I see expand the instruction set. So a good idea from Camilo. So, and that's usually given the name custom instructions. Okay, so we're gonna put some extra instructions in that maybe aren't super generally useful, but they're useful to the exact computation that you want to do. Okay, so let me draw what this looks like. Most FPGA soft processors are classic 5-stage RISC pipelines. Well, maybe I shouldn't say RISC, there's classic 5-stage pipelines. So soft processors, because their main reason to exist is to control hardware units, to do housekeeping, etc. If you need really high performance, you're probably going to get a hard processor. They don't tend to have really complicated microarchitectures. So they're usually a 5-stage pipeline. So fetch, decode, some ALU operation, memory. Oops, let me clean up my writing a little bit. And right back to the register file. Okay. So what a custom instruction normally does is it's expanding essentially your ALU. So you've built something that is your execute stage or your ALU stage. So if you decoded your custom instruction, so you find that the opcode matches the custom instruction that you just put in. So the soft processor reserves certain opcodes for you to use. And you go off and it goes to some special hardware you built and does whatever that hardware was designed to do, and then basically goes back into the pipeline. So it goes into, I'm showing here, the memory stage. Okay, so what's this useful for? So it's useful for basically fine-grained operations. Okay, so an example of that would be CRC, certain encryption operations. CRC is a cyclic redundancy check. It tends to involve a whole bunch of XORs. It's like a generalization of computing parity. It's how you do error correcting codes. You can do it on a regular processor, but what you usually wind up having to do is you have a whole bunch of XORs and shifts and OR operations and so on to construct what you want. And you can build hardware that very efficiently does shifts. Shifts are just basically you wire things up differently if it's a fixed shift. And XOR, you program the truth tables and the lookup tables. You can make very efficient hardware for cyclic redundancy checks that does, again, the shifts and these XORs. Encryption looks somewhat similar to that. Encryption basically tries to scramble your bits, and it does that with things like XOR, lookups into little RAMs, shifts, and so on. It basically is just trying to scramble the bits in all sorts of ways so that no one can guess what you're trying to send. It's scrambling them in a clever way so that you can undo it at the receiving end. Again, processors can do these operations, but they tend to involve a whole bunch of instructions to build up what you're trying to do. And when you map them to logic gates and small block RAMs for things like encryption, you can reduce the instruction count a lot. So that's where custom instructions have had kind of their greatest success, is these kinds of instructions. So the reason they're good for fine-grained operations is kind of that they're not very good for coarse-grained operations. So what I mean by that is let's go back up here, and I said one of my previous grad students made a matrix decomposition engine. So and that did a whole lot of work, right? So the basic element of what it was doing was taking entire pieces of rows and scaling them and adding or subtracting them to other rows and doing that over and over again. So that's a pretty coarse-grained operation. If we tried to make an instruction that was do the following to this whole piece of a row of the matrix and compare, and then add that or subtract that from this other piece of a row of a matrix, that would be a very coarse-grained operation. That doesn't fit this style very well. Even if I know that all I ever want to do is do matrix decomposition, can't really fit that into a custom instruction well. So why? Why can't I fit that into a custom instruction well? I already know what I want to do. Why couldn't I just make an instruction that takes 100 elements from a row of a matrix, scales them, subtracts them from maybe the next 80 rows underneath it? So I just encoded a huge amount of computation. Why does that custom instruction not work very well? Let's see. So complex operations takes too many cycles to operate. Yes, those are good answers. It's not that I couldn't, we're going to see other ways to organize that, but basically it doesn't fit into this custom instruction very well, because this custom instruction is basically too closely coupled to the soft processor pipeline. So we have the number of ports, so the amount of data that we can get to this custom instruction. Let's see if I can find a proper highlighter here. Okay, so let's look at this custom instruction here. So the number of ports we have from the register file defines how much data we can get to this custom instruction. And this whole CPU is generally built with a very limited number of ports to the register file, right? Register file is centralized storage. It gets expensive to add many ports. And an ALU normally only reads two operands, so it doesn't need that many ports. If our custom instruction needs some huge number of ports, it just doesn't fit into the processor pipeline. We only built a very limited number of register ports. Probably 2 read ports and 1 write port for the simple processor that I've shown here. Okay, so our ports are limited by the register file. And you can say, well, go change the register file, but now I'm basically changing the whole processor. The whole idea was I want to just define a custom instruction and it works with my existing processor, so it wasn't too hard to design. But I've got a mismatch if I try to do a coarse-grained operation. It needs a lot of data from memory, and I don't really have an obvious way to get that to it. Another one is it's going to take too long, which Jehu pointed out. So if it's a coarse-grained operation, we're going to have to stall the processor if it's a long-running operation. So you can do that, but it basically reduces your parallelism. This custom instruction now could take many cycles. It's perfectly legal, but we don't want to make an incredibly complex soft processor because that's going to take too much area. So we're not going to have the rest of the processor continue executing while the soft processor or the custom logic is computing. So basically, if this custom logic takes a long time, we're going to stall all of the operations that come after it, which is functionally fine, but it's reducing our parallelism. Our processor is just waiting for the custom instruction to finish. So this is kind of a cool idea, and it's had some success, as I said, in this limited domain, primarily in CRC and encryption. One of the challenges you always have when you're programmable is if it's too good an idea, then it might get copied by fixed devices. So some hard processors now have instructions in them that make them better at CRC and encryption. So if everybody wants the same custom instruction, or many people do, then the regular processor vendors will actually eventually put that in the instruction set. So the other thing you'd kind of like in custom instructions is if everybody wanted a different one. And it turned out that the ones that were most successful were kind of generally useful enough that a lot of the hard processor vendors modified their instruction sets to put those in. So that took a few years, but that's now happened. Let's see. I see there's a question from Camilo of, does all the data have to come from the register file, or can put a streaming input and output as a fake register we can read and write to? Yeah, so that's a good idea. So basically, Camilo's pointing out, well, why do I have to hook this custom instruction? So let me highlight this again. So why do I have to hook this custom instruction up to the register file? That's the way I hooked it up here. But that seems like that's limiting me. I can't get enough data to it. If it takes me quite a few cycles to operate, I'm locking up the whole processor because you don't have the control to try to figure out when is the custom instruction going to write back, etc. So the solution to basically make a higher performance augmented processor is to decouple things. So when you don't take your data from the register file, in theory, I guess you could still have a custom instruction that connected you to some block RAMs or off-chip memory or something else. So that theoretically could be done. But basically, it doesn't fit this kind of fine-grained interaction. The idea of a custom instruction is you're right in the pipeline. It works best if you behave a lot like a regular ALU. Take a couple operands, compute an answer in one cycle, put it back in the register file. So, you're a new instruction that behaves a lot like the other instructions. So to Camille's point, that is a good idea. Let's give our coprocessor access to more memory, allow it to operate more independently, and then we can get a bigger benefit from it, and we can get more parallelism. But what people have done is they haven't done that as custom instructions because it's hard to integrate something like that as a unique instruction. And instead what they've done is they integrate those typically as coprocessors. Okay, so that's the other way that you can augment processors. So what does it look like? So they're not as closely coupled. You have your microprocessor, could be a hard microprocessor, could be a soft microprocessor, and you create whatever custom hardware you want, you call it a coprocessor. And that coprocessor can connect to memory. So that could be block RAM on chip. It could be off chip memory. It could be both. So this could be a huge amount of memory if you want it. And we connect them not right into the processor pipeline as we did with the custom instruction. Instead, we connect with a bus. And usually you'll use a standard bus. So the most common standard bus is AXI, which is used by Xilinx and somewhat by Intel, and also used by a lot of ASICs and ARM. And the other common bus in the FPGA world is Avalon, which is used only by Intel FPGA, so not as widespread as AXI, but still pretty widespread. They both behave pretty similarly. They're just slightly different protocols. Okay, so you have a coprocessor, and basically we're less coupled to the microprocessor. And that's given us some advantages, right? We can get it more memory because we can have our own connection to memory, either block RAM or off chip or both. So we've got more memory, we've got more memory bandwidth, because that could be a wide connection, right? So that could be many, many wires, could be hundreds, could be thousands. So it might be a lot of bandwidth. We get more concurrency. So if this coprocessor, if the microprocessor sends it a command and the coprocessor takes 10, 100, 1,000, 1,000,000 cycles to execute, the microprocessor doesn't have to stop, okay, because they're more loosely coupled. It can basically just send it a command, and then the coprocessor can interrupt the microprocessor when it's done, or the microprocessor could check some status register, but we don't have to bound how long the coprocessor takes in order to avoid messing up the processor pipeline. So basically this leads to bigger potential speedups. And they also don't operate in lockstep. So basically that's why we're getting this bigger potential. The more loose coupling is helping us. They can be at different frequencies. Okay, so the coprocessor can take many cycles. That's one form of being decoupled. It could also be at a different frequency, which means that you can kind of optimize each one separately. So that can also get you more performance. Okay, so I'll give you an example of this style, and then we'll take a break. Okay. So this is an example that came from particular project in my career at Altera. Okay, so I'm going to go through how we attacked developing a very complicated IP core for memory interfaces. Okay, so memory interfaces are basically, you know, DDR. There's DDR, then DDR2, then DDR3, then DDR4. They're all very, very similar. They change the electrical specs a little, they change the protocol a very small amount, but they just keep getting faster and faster, okay? And memory interfaces are, you know, one of the most important I/O protocols. You want to get high bandwidth, you want to get low latency, and an FPGA has an additional bunch of constraints. So they're programmable. So we want to be able to connect to all sorts of different kinds of memory. FPGAs don't typically build an interface just to one kind of memory, you know, DDR3 or DDR4. Usually you can reuse those programmable IOs for a whole bunch of different purposes, because people use different kinds of RAM, or they might not use RAM. They might use those IOs for something else. So that makes actually designing FPGA memory interfaces extra tricky, because they have to be more programmable than they would be in other chips. It is a complicated piece of memory interface design called calibration. Okay, so let me show you what a memory interface looks like. So you have in an FPGA. So you have a design. It talks to something called the memory controller. And the memory controller basically understands the protocol of, you know, I want to read, I want to do a write. That's basically it, right? So it understands how to turn those requests into the low-level signals that the lower-level commands that the RAM actually understands. A RAM doesn't actually, it needs to be told, bring the following row into the sense amps, and now you can read out a piece of that row, which is called a column read. So the RAM actually has a lower-level protocol. The controller bridges that gap. And the controller can also decide on how to order things for more efficiency. The controller talks to the PHY, or the physical access layer, and that's the one that deals with all the complicated timing, well, particularly timing, the timing and the lowest level interface details. Okay, so all this piece that I'm showing you, these two layers would be on the FPGA. Okay, so almost all designs are going to talk to, you know, one or more memory, off-chip memory chips. So this is your design. You don't want to worry about this. You just want to instantiate some intellectual property core from the FPGA vendor, and that intellectual property core internally has got these two components. It's got a controller and it's got a PHY, and it's going to link you up to the off-chip memory. Okay, so on your board, you now have off-chip memory. As I said, there are a whole bunch of different variations of DDR. The version that my group primarily worked on was DDR3, so I'll use numbers from that. Now you can buy DDR4. It's basically the same, just the clock rates are higher. Okay, and these are pretty fast. So for DDR3, a typical frequency would be that you're sending data at 1.6 gigabits per second per pin. So every single pin connected to that can send data at 1.6 gigabits per second. So I'm kind of digressing a little bit, but it's kind of, there's some interesting aspects to this, this interface protocol too. So this is called the source synchronous interface protocol. That's basically one of the two ways you do high-speed I/O. Source synchronous means you send the clock beside the data. The other way you can do it is with serial I/O, which we'll talk about a little later in the course when we get to some examples of those blocks. Okay, so what does this look like when we get down to the lower level details? The FPGA is going to send a signal called DQS. DQS means data strobe, okay? It's like a clock, but a strobe is like a clock that can start and stop. So you don't send this clock when you don't want the RAM to do anything. That saves some power. But otherwise, you're basically sending a clock to the RAM chip, okay? So we send a strobe signal, and we also send the data signal. And in, whoops. And we send several data signals in DDR. So typically 8 go along with the DQS signal. And the idea is that I can use the edges of this DQS signal, whoops, This is actually where it's not that helpful that it's deciding to fix my drawing. How do I undo that? Let's see. I think in the break, I'm going to try to figure out how to stop.
You can just press Control Z and it will undo it.
Oh, thank you. Okay, so I tried to do, I did some drawing there where I made it intentionally more messy, so I'm hoping it doesn't recognize it as boxes. Okay, so the idea of a source synchronous interface like this is I'm sending the clock, or in this case the strobe, and the data, and I'm aligning it so that, let's see if I can draw this in a different color. I'm aligning it so that I can actually use the edges to sample the data. Okay, so, and DDR, the double data rate, comes from the fact that we use both edges of the strobe. Okay, so both the rising edge and the falling edge, we're going to sample the data. So it's important that that transition is when the data is stable. So we need the strobes to transition away from the edges of the data. And memory interfaces are designed to keep memory chips really cheap. You make a lot of memory chips. So all the complexity is you try to push back into the controller and the PHY. And this memory chip just tries to do relatively simple things. Okay, so we send the strobe and the data to the memory. Properly aligned so that the memory chip can just use the data strobe to sample the data. And we need to adjust the delay of each signal until the transfer is reliable. Okay, so what do I mean by that? There are a whole bunch of delays in the circuit board, in the DRAM chip, in the FPGA. There are on-die variations. There are changes in delay that happen as the chips heat up, etc. It turns out if you analyze the worst case of all those delay variations, that this problem is basically impossible. Okay, there's no valid window. You can't find any spot where you can arrange this strobe edge so that you can reliably sample across all the memory chips that might be on the board and their variation and their temperature and voltage variations and so on. So, so what do? Well, you have to calibrate. Basically, when the FPGA powers up and you have this IP core and it tries to talk to the DRAM chip and it starts adjusting the timing of all these signals until it can get reliable data transmission. And it actually can also, it has to adjust them somewhat while the device is operating as well. But most of the calibration occurs when you power up the design. These data paths are not 8 bits wide. So the data path is typically 64 bits wide. But again, in FPGA, you can ask for a 16 or 32-bit memory interface too. So not always 64 bits, but that would be common. So data path is usually 64 bits wide. But an FPGA has to allow, again, more flexibility. And they're fast, 1.6 gigabits per second per pin. So that's what you're getting at the pins. And even higher when you move on to DDR4. Okay, so that's our data path. Data path is fast, relatively wide. The control of, what are we trying to do? How are we going to adjust the timing of these edges is actually quite complicated. So it's a complex calibration algorithm. And that calibration algorithm isn't fixed. Like, it tends to change. As new memory protocols come out, as faster chips come out, as new FPGAs come out, you have to change your calibration algorithm. So it's not something you can sort of varnish and say it's done forever. Oh, thank you for the suggestion of unclick inked shape. Okay, so I just turned that off. Thank you. Okay, so what is the architecture? So the architecture we chose was a microprocessor plus coprocessors. Okay, so so why? Well, we have a fair amount of parallel hardware. 64 bits wide is typical. It needs to be fast. Okay, so we're not going to have a microprocessor that can keep up with that kind of speed. So it can't be in the data path. That's going to have to be a coprocessor that can manage that speed of moving data across the memory interface. But the control is intimidating. We're going to have a complicated calibration algorithm, and it's going to change a lot. So that's going to be challenging to commit to hardware to put that in the finite state machine. So we split it into two pieces. Data path is going to be dedicated hardware, and the control is going to be a microprocessor directly wired up to that, which is why I'm using it as an example here. Okay, so what do we do? So we use Neos, which is Altera or Intel's soft processor. And what do you think? Should this be like custom instruction, or should this be a coprocessor? Probably a hint is what I wrote on the slide. So this is not going to fit into a custom instruction very well at all, right? We have a lot of data to move. So we need to do it with the more loosely coupled model of a coprocessor. So I've got a processor for control. And now I need to make my coprocessors. So we made a few. So we made a write coprocessor. We made a read coprocessor. And both of those are wired up, straight to the pins of the FPGA. They can take control of them, and they can talk to DDR3. So they're wired up right to off-chip memory. They're also wired up to an on-chip bus. Okay, so this was the Avalon bus, but it could just as equivalently be AXI. And by writing to certain addresses on that bus and reading from them, the Neos processor can control the system. The Neos processor also we need some on-chip RAM. So that's where we can store instructions to tell the processor, what to do, and also where we can store results from this read and write coprocessors. So for us to make this calibration algorithm work, we need to read and write at speed. Okay, we can't slow things down. We need to come up with how to adjust all of these delays to talk to the memory interface at full speed. Memories also speak in bursts. So you actually send and receive multiple data words. So you're sending entire bursts of data to the RAM, and then you can read back something from the RAM and see if you get what you expected. You don't actually know if the write worked or not. All you can check is whether you get back the data you expected. If you didn't get back the data you expected, something's wrong, but you don't know what's wrong. Maybe the read didn't work, maybe the write didn't work, maybe both didn't work. So that's where the calibration algorithm can become, reasonably complicated to try to figure out what to do. The IP core also has quite a few degrees of freedom of how it can adjust timing. There are delay chains on the FPGA. So it can basically add and subtract small delays from the individual signals up here, either the strobe or the data. It can change the clocking. So it basically is also controlling the phase lock loops that are generating the clocks that you're using to talk to the memory. So it actually has a bunch of different things that it can try as well. So with this architecture, the coprocessors are fast enough. They can handle the full speed of this particular DRAM. They can handle 12.8 gigabytes per second transfers. Okay, so when you add up 64 bits times 1.6 gigabits per second per pin, that's the data rate you're getting. That's way beyond what you're going to have a microprocessor push instruction by instruction. But what the CPU does is it can set up the tests. So it writes to some registers that are inside. There's little memory mapped registers inside of these coprocessors. The microprocessor writes to them to send them commands, and it reads from them to see what happened. Okay, so the CPU can set up tests. It can look at the data. The data comes back and can get put into this on-chip RAM. And now the processor can relatively slowly look at what happened and decide what to try next. Okay, so it analyzes pass, fail. It can try to analyze more detailed patterns. So it can try to look for, is there some pattern of what's happening? So it can try to figure out what should I try next. It can try the next option. Etc. Okay, so that's the architecture that we chose. This project was actually moved to Altera Toronto because memory interfaces were proving to be like a big problem for the company. So this wasn't the first attempt to build IP cores to do this. We already had IP cores, but they weren't working that well. So this was a big decision of what architecture were we going to choose. So the other architecture we could have chosen is to go all hardware. Okay. And that's actually what the previous generation of IP cores for this did. They didn't have this structure of using a microprocessor to control coprocessors. They basically did it all in Verilog, built big finite state machines that were directly controlling certain hardware units. And they hadn't scaled to the highest frequencies. So they actually couldn't reliably calibrate to DDR3 at this frequency. So the calibration algorithm was going to have to get more complicated. So this all hardware solution needed some updates as well. So I should have set a poll for this too, but you just type in the chat. How big do you think the finite state machine to control basically a simpler version of this, like the prior generation was when it was just written in pure Verilog? So you got a state machine mixed in with some of the data path units. How big do you think it was? So how many lines of Verilog? This is one where there's no reason you would know this. So this is just to make you take a guess to think, how big can a finite state machine get? 30,000, 500, 10,000, several thousand. Wow, you guys are actually really good guessers, I have to say. So some of you might want to go and yeah, I don't know if I should encourage you to play the lottery or not, but for me not giving you enough information for you to have any real hope of answering this question, these are remarkably good guesses. So so the actual number, which shocked me, but maybe doesn't shock you guys as much, is it was 20,000 lines of Verilog in the FSM. So there was more in the data path, which had kind of gotten merged, wasn't as cleanly separated from the SSM as well. And this was problematic in all sorts of ways. This algorithm had to be updated all the time for new chips, new protocols, higher speeds. And you can imagine that if you have a 20,000 line FSM, updating it is like not for the faint of heart. Like it's really easy to break that. The other problem is actually the FSM can start getting slow. It actually can be a problem to get timing closure on this. This architecture kind of cleanly separates the high frequency logic, which is here, from the lower frequency logic. Sorry, I'm not going to use that. See if I can actually undo that. I think I'm learning not to use the pink. The pink is not very, yeah, it's hard to read. Sorry about that. Anyway, it separates the high frequency logic from the lower frequency logic. With this big FSM, even though it doesn't have to run as fast as the data path, it was becoming a problem for it to keep up. So this not only was really hard to maintain and update, is actually larger than the whole microprocessor. This NEOS design, so NEOS, depending on exactly what you ask for, takes around 1,000 lookup tables and registers. So it's not, it's bigger than a typical finite state machine, but not ridiculously huge. And this was basically, you can choose how high a performance of a soft processor you want. We could use essentially the lowest performance version because it's just controlling these co-processors. So this was a win in a lot of ways. It basically made the developers far more productive and agile, and the control was so complicated that this is where a microprocessor is good. When a control gets really complicated, they're actually very efficient because they store that control in just instruction words. Let's see. Okay, so let me give you one other example of where these augmented processors can be quite helpful. So another case where they're very useful is the slow path in packet processing. Okay, so a big market for FPGAs is wired communication. So I've talked some about wireless. Wireless, a lot of that is filtering. They're also used a lot in wired communication, where you're doing a lot of packet processing. And that is really fast. Data rates keep rising faster than Moore's law in wired communications. So the common case for a packet is it has to go through all hardware, right? So your typical packet goes through hardware, very wide buses, lots of parallelism, deeply pipelined as fast as you can make it, and it's a challenge to make it fast enough. So most of your packets, they go through a hardware fast path. Okay, and that's basically streaming hardware with a high degree of parallelism and pipelining. But there are some more unusual packets. Okay, so there are management packets. So there are ones that basically tell you to update your routing tables, which are much less frequent, but also much more complicated. And there can be other exceptional packets, error conditions and so on. Things that are not that common, but the processing for them might be quite a bit more expensive. So those ones can be kicked to a slow path in hardware. Or sorry, slow path in software. Now in this particular case, packet processing moves so much data that this can still be too fast for a soft microprocessor. Okay, so you can try to make a faster soft processor, and people do that sometimes, but this is one of the places where a hard microprocessor on chip can be very useful. Okay, so hard microprocessor, so commonly ARM, and these are, depending on which chip you're talking about, 2 to 4 cores and 800 megahertz plus. Whereas soft processors usually run at 300 megahertz. In the latest chips, maybe that's rising to 400. You could make many cores, but you're going to have a lower IPC and a lower frequency. So for this kind of case, it fits well into a hard microprocessor on chip, which can handle these exceptional packets without having to put a Xeon or some other kind of CPU in the same system. You can just do it on chip. That's all I have to say about augmented processors. Well, I guess maybe I have one last thing I'll say in terms of augmenting a microprocessor. We talked a bunch about coprocessors. The last way or common way that people will augment a microprocessor is to make it vector. Okay, so make a vector microprocessor, which is basically a microprocessor with Simdi. So that's a technique by which, if you've got a lot of data parallelism, you can make your processor more efficient. As we talked about earlier, it's one of the things that GPUs are doing something very close to that. You can do it on chip as well with soft processors. You build one control unit and use it to control many functional units. So yeah, another form of Simdi. There's a company called Vector Blocks that started out of UBC, and it makes IP to do this. So to make soft vector processors on FPGAs, the gain efficiency by doing Simdi and by adjusting the architecture of the processor to your computation. They lose performance by still being a processor. They have register files, they have instructions, and so on. So that it's not clear that is efficient enough to do the heavy lifting in your design. So That particular company is trying to move the heart of the processing that you do in an FPGA to use vector soft microprocessors. It is significantly more efficient than using a regular soft processor, but it's still not clear it's efficient enough. It's not as efficient as streaming hardware. So this is, in my opinion, something that is good for a part of your computation that has reasonable performance demands. But if everything you're doing fits very well into a vector microprocessor, then you should start thinking about, should I buy a GPU? Or should I buy a hard vector microprocessor, because you can buy processors with Simdi that are not built in an FPGA. Okay, so with that, we'll take a 10-minute break, or how about an 8-minute break, and we'll start again at 5:40. We're more than halfway through, so I didn't actually manage to do a break in the middle. So if you're going, wait, we're on track for a really long lecture, it's not that bad. And I'll be here if you have any questions. So, but otherwise, feel free to go wander off until 5:40. Andrew, can you hear me?
Yeah, I can hear you.
Okay, thanks. I've got a sufficient number of buttons and mute options that I wanted to check. Thanks. Okay, so we're back. And I used a little bit of the time while we're off to write a few words. So the next computation style, and one of the last ones we're going to talk about, is called Cellular Automata, which someone actually raised earlier. So that's great. So doing the reading. So a lot of computations operate on a grid or a lattice. It's kind of mean the same thing. It just means that you're operating at different points in space. A common case for this would be partial differential equations. So if you're trying to solve partial differential equations, either two-dimensional or three-dimensional space, you can think of, I'm trying to find the value of, say, voltage at various points. And the way I'm going to do that is to apply operators at those points to calculate what my voltage is, for example, from nearby voltages. So an example of this is finite difference time domain. So that's one style of physics solver, which basically takes differential equations and turns them back into difference equations. Remember, a differential equation is it's a difference equation where you take the limit as the difference becomes infinitesimally small. If you can't solve that problem analytically, you can't work out the calculus equation, which usually you can't for complicated geometries, you can solve it numerically by making the difference finite, so small but not infinitesimally small, and basically solving the difference equations repeatedly to find the solution, a numerical approximation of the solution. So let me show you what I mean by that. So we're electrical and computer engineers, so we work with Maxwell's equations a lot. So you can define, well, you can't solve some complex field problem using vector calculus. What you can do is just define a grid. So here I'm showing you a little cube. This is a tiny piece of a lattice that would define the volume where I'm trying to solve for field quantities. So let's say I'm trying to solve for the electric field and the magnetic field. So I've got time varying electric and magnetic fields, and I want to solve for them throughout some space, maybe an antenna. A form of physics solver for that will basically, let me change the color of my pen. Let's see. So let's say that my electric fields are red. Okay, so you can define, say, the y-directed electric field at these points. And I'm just showing two, but you'd actually do this in many points throughout space. So those are EY. And I might do purple for magnetic field. I might define the magnetic field as coming out here. So I've got a certain HX that's going in the X direction at that point. And I'm not going to write all the equations, but basically I can compute H of X at a certain time step from my electric fields at the prior time step, because magnetic field is related to the rate of change of the electric fields around it. And yeah, I'm not going to write all the equations out because you get a whole bunch of them pretty quickly. But the idea is I could step in time. From time equals 0, I would basically assume a certain set of electric fields. And from those, I can calculate throughout all these grid points what are the resulting magnetic fields. From those magnetic fields, I can then advance time a little bit and compute what are the resulting electric fields, and keep doing that for some particular time. And I'll eventually get what were the electric and magnetic fields throughout this whole volume through some period of time. And that can be useful in a lot of different things. So let me quickly show you a picture that is better than what I can draw. So this is a more complete picture of a little piece of a lattice for a finite difference time domain solver. This shows, I've got a bunch of different directions of electric field and magnetic field. And yeah, hopefully you believe me that you can take the differential equations, discretize them, and you can basically write update equations of how does HX get updated based on the electric fields around it and how they change over time. If I solve these difference equations throughout space, that's what I'm showing in the bottom subfigure down here, I can work out in some interesting geometry. And this is a horn antenna, so there's a particular kind of antenna. And I'm trying to work out what does the radiation pattern look like. So this is the radiation pattern. Where's the energy coming? I'd like it to be directed sort of in a nice narrow beam so that I can communicate with some other tower or build a radar system, something like that. And basically by stepping forward in time across every point in this whole volume and updating the electric and magnetic fields in sequence, I can work out in both space and time what do the electric and magnetic fields look like for this particular geometry. And this is one that's way too complicated for you to solve analytically, just by trying to solve Maxwell's equations with pen and paper. All right, so hopefully that gives you some idea of a particular example of a lattice problem. But you can write lattice problems like that, not just for electromagnetic solvers, but pretty much any physics solver. So mechanical engineers can do this too for Navier-Stokes and the kinds of differential equations that they work at. All right, so how does this relate to computation? So we can think of, let me change my pen color back. So we can think of this as the data and the operators are both distributed in space. Okay, we can think of them as being at grid points. Okay, so when I talked about how spatial hardware really likes having the data distributed because we can spread it out through our chip and everybody gets access to the data that they need right beside the compute units. These cellular automatas are really nice for spatial computation because we can naturally distribute the data. The data is distributed in space because we're solving a physics problem. We can distribute it in space in our chip. And the updates, because of the nature of basically every reasonable partial differential equation, the updates only look at data around you. Okay, so this particular magnetic field is updated based on the electric fields around it, not the electric fields halfway across the grid. So the operators, in this case, we'd have to take the differences between a few electric fields around us, and a few sums. So those are the operations, but those are all local too. They only need to look at data that's right around them. Okay, so this actually fits really nicely to spatial computation. So we can implement it in space in a very natural way. The data is data, and the update hardware for a particular grid point are co-located. And we only need to grab data from the grid points around us in order to update our own data. Okay, so what are the positives? So the positives of this, only local communication. And that's really just a property of, if I'm using this to solve physics problems, that's really a property of physics. That's just the way differential equations work. Your quantity is updated from the changes in things around you. Okay, so that only local communication is really good. That allows us to have low wiring delays and be fast. It means that we don't have any centralized bottlenecks. We don't run out of wiring, etc. Okay, we also have only local storage. Okay, so those two things together are great. Makes this very fast. Okay, think of any negatives. So far that all sounds good. Is there a negative to do it, thinking about the computation this way? So if I want to model a complicated geometry, I'll go back and show you this antenna. I need quite a few grid points. And this antenna is moderately complicated, but you can have things much more complicated than this. Early in my career, I wrote field solvers, so I worked for a CAD company writing them, and a lot of our customers were doing things like building MRI machines. An MRI machine is much more complicated than this. The magnets have very complicated geometries and so on. So you need a lot of grid points to represent that accurately. So that's kind of a hint. Any negative, when you start thinking about the problems that people care about solving quickly, don't tend to be small, they tend to be big. So is there a negative as we make this grid large? Yeah, so I say a couple of comments on this. Yeah, you can run out of hardware. So, blazingly fast, if we could basically give every grid point its own update hardware and store its state in one particular spot in the FPGA, then this is extremely fast. We could basically move to the next time step in just a few clock cycles, because we just have to run these operators to update the grid points. We can move right on to the next time step. So it'd be unbelievably fast. But the problem is, for a big problem, we're going to run out of space because we have a chip that has a certain amount of capacity. Once we can't implement all the operators and all the storage that our grid requires, it won't fit, okay? Okay, so we can run out of storage or run out of space, both compute and storage for large grids. And unfortunately, that's usually what people care about, because those are the ones that take a long time to run. There was a paper, let me give you an example of this. You can apply this to things other than physics solvers. So Andre de Haan, who's actually one of the editors of the Reconfigurable Computing book that you've read a couple of chapters of so far, has an interesting paper from a few years ago where he basically took FPGA placement. And FPGA placement for a big design actually takes quite a while. So choosing where do I put all the lookup tables, where do I put all the registers, and so on, it gets slow. It can take many hours for a big design. So that's annoying. So he looked at FPGA placement, and he simplified the algorithm, simplified it down to neighbor swaps. Okay, so that means he's decided where to put all the lookup tables you need. He's chosen a lookup table for everything, and he just has neighbors communicate to decide, should we swap or not? If we swap, would we reduce wiring? That allowed him to basically make local operators, cellular Autonoma operators, that just evaluated, should I swap with my neighbors or not? So I've got 4 neighbors, should I swap with one of them or not? It was very fast, but his challenge was that because those operators each take several lookup tables and registers and so on to to make, to decide should I change my location or not. He couldn't handle really large capacity problems. So only 2,000 lookup tables could be placed. Okay, so his hardware accelerator could take as input a net list of up to 2,000 lookup tables that represents your design. And it can place it really fast because he uses all these local operators to decide who should swap with whom, and you can repeat that many, many times till everybody goes to keep swapping till they get to a pretty good location. But in order to place 2,000 LUTs, he needed a 1 million logic element or lookup table FPGA. So that's the problem. Basically, if you have a really big FPGA, then this technique would allow you to do placement of a fairly small FPGA design really fast. But what you probably care about is placing a really big FPGA design. So that's the problem with cellular autonoma. If the problem gets big, if you're in the happy situation of your problem never gets big, and you can map it to this, it's very efficient. There is a solution to this. So something called folded cellular automata. Okay, so what that does is it just implements a piece of the grid. It can't implement all space. Okay, so implement a part of the lattice, or we could call that the grid. They mean the same thing. And then what we're going to do is we're going to stream data through it. So we can't represent, my example that I showed earlier, we can't represent every point in this antenna. We're only going to represent, maybe we can represent a certain fraction of them. And we will basically stream data through a smaller grid. So we can model maybe this part of the antenna first, update all of its electric and magnetic fields, and then we basically have to send that data back through and compute this part of the grid. Send data back through and compute this part of the grid. So we get something that is partially parallel and partially sequential. Okay, so we stream data through it. And into global storage. So positive of this is it can do bigger problems. The negative, so I see a couple of interesting questions. So what's the optimal size for cellular autonoma? So I guess basically with this architecture where you're folding it, like you're basically building a certain amount of the grid, you would build as much as you could. Like you are faster and more efficient if you can do as big a chunk of the grid as possible, which is generally still going to be a pretty small part of the grid. Maybe it's 1%, but you will get better performance if you do 1% than if you do 0.5%. So you're basically going to fill the chip is what you usually do. It's basically you've gained capacity by doing this. What you've lost is it can have high memory traffic. So if we think of electromagnetic problems, you would stream in a whole bunch of electric fields for a part of the grid. You would get a whole bunch of magnetic fields for that part of the grid, write them out to memory. And then you would stream in the fields from another part of the grid, get a whole bunch of magnetic fields for that part, write them out to memory. So there's actually a lot of memory traffic. So we've lost some of our nice distributed memory. And instead we have a lot of traffic coming in from off-chip memory probably, because this is usually pretty big. This becomes a lot like streaming hardware. So it's still a useful way to think about it. But once you think of folded cellular automatas, it is related to streaming hardware. It's just the streaming hardware is essentially computing a portion of the values on this lattice or grid. There's a question, is high memory traffic a negative for regular cellular automata? If you can fit the whole lattice or grid on chip, you have very little memory traffic. Everybody's just talking to their nearest neighbors. So no, if you don't have a problem with memory traffic if you can get the whole lattice or grid on chip, but for a big problem, you're probably not going to be able to do that. And then memory traffic does become an issue. There are some optimizations that you can try to do to reduce memory traffic some. For the particular example I showed you, where you're computing electric and magnetic fields. So you compute electric fields at a certain time step, then you update, you then compute the magnetic fields for the next time step, then you compute the electric fields for the time step after that, and you kind of ping pong through time that way. That's how you actually solve Maxwell's equations using finite difference time domain. You can do things like bring in the data for a part of the grid, as much as your chip can handle. Compute not just the magnetic fields for the next time step, but compute the magnetic fields for the next time step, then compute the electric fields after them, then the magnetic fields again, and do that for a while. So that actually can reduce memory traffic because you're going to do more time steps, but only for a part of the grid. You can only go so far there because the processing elements near the edge basically can't compute after a while because they need data from other parts of the grid, and that hasn't been computed yet. So there is a trade-off. You can go forward in time and compute more data, and that reduces your memory traffic, but gradually your processing elements near the edge have to stop computing because they need data that hasn't been computed yet. So you gradually lose parallelism. But you can explore that trade-off space, and that will cut your memory traffic some. And hopefully that is not, that's a somewhat subtle point. So hopefully I didn't confuse you by telling you that. Okay, there's another question. Isn't it possible to have a cluster of FPGAs for regular cellular automata because each grid point only has to communicate with its neighbors? Wouldn't be a huge communication delay between FPGAs? Yeah, that is true. Because the communication is so local, you could split it across chips pretty well. There's less communication bandwidth between chips than there is within one chip. But you're right, the communication in a cellular automata is quite local, so it's probably going to work pretty well if you split it across multiple chips. So if you care, if cost is no object and speed is everything, that'd be a reasonable thing to do. Obviously, it becomes an expensive system if you every time your problem size doubles, you have to buy twice as many chips. So it's a reasonable thing to do. It basically trades cost for time. And there is a company that actually, this finite difference time domain for electromagnetics, there is a company that does exactly this with FPGAs. So this particular example is not actually a very hypothetical one at all. And they do use multiple FPGAs. So to get higher throughput, they do exactly what Madi is suggesting. Okay, so almost done with compute models. So let's talk about M. Or no, I'm actually up to K. Sorry, I skipped a whole bunch of the alphabet. Okay, so K is multi-threading. So we already talked about multi-threading in streams, but it's more general than that. You can do multi-threading with all sorts of different kinds of hardware. It just means that you're going to reuse your hardware with multiple instruction or data streams. Okay, so why would I do that? Any ideas? Why would I multi-thread? Because we talked about one of these. I guess maybe it's a hard question because it's kind of vague. But basically, one reason you multi-thread is to cover latency. So we talked about that essentially for loops and streaming hardware. We have a certain latency to compute an answer, and that's stopping us from getting more pipeline parallelism. If we multi-thread, we can tolerate more latency and allows us to pipeline deeper. So that was helpful for loops. It's used in processors to primarily to tolerate memory latency. if it takes a long time to go to main memory and get an answer, you can just switch to some other computation that doesn't depend on what you're going to get back from memory and make some progress on it. So that's one of the ways that multi-threading is used in processors, and you can use it in your hardware in exactly the same way too. Okay, so that's one main use of multi-threading. The other one, which we also talked about the other day, was to maximize use of expensive hardware. Which is kind of related to latency too. Like if your hardware was just going to sit there waiting for data from main memory, then if you have some more, if you can set another thread of data, you are reusing the hardware. So I guess these two things are not completely separate. Okay, there is some cost to add multi-threading. So you don't want to multi-thread for no reason. But it's, the cost doesn't have to be that high. So we saw how we can use C-slow retiming to multi-thread streaming hardware, and the cost isn't that high as long as you haven't run out of registers yet. Processors, many of them use something called hyperthreading, which is basically if they can issue instructions from more than one stream or thread to their execution units. So they try to keep their execution units more busy because their execution units are expensive. Okay, so this can be done with anything. Okay, so microprocessors definitely use this. We can do it with streaming. And shared operators, anything. There's all sorts of things that can actually use multi-threading. Okay, and the last point I'll make is basically something that the reconfigurable computing book calls hierarchical composition. All that means is that you often can't describe your whole system with just one compute model. There may be a dominant compute model, that's what you're using for most of your heavy lifting, but you'll often combine different pieces and styles. And that's natural in hardware, right? That's how we compose modules in hardware description languages. So we can combine multiple pieces or styles. And kind of use the best tool for the right job. When you do that, you have to decide how are they going to communicate. So there's a whole nother set of problems, which I'm really not going to talk about in any detail. But we can communicate with either dedicated links, where we just wire one thing to another. We can communicate with shared memory, right? Which can create a central storage bottleneck. So if you know that you only need to communicate with one thing, dedicated links are more efficient. We can also build networks where there's some muxing and switching in them. So we can send messages on a network or a bus. So when we looked at coprocessors, we talked a bit about, you wire these things together typically with buses. We talked a little bit about communication. But as you start composing things, that becomes another part of your design decision of how to wire everything together. Let's see. Okay, I think I answered all those questions. All right, so I guess I'm not going to write this down, but I guess my summary of this would be, we looked at a lot of different programming models. The ones that are kind of the most hardware friendly tend to be the streaming ones. So streaming is very hardware friendly, can be very efficient in FPGA. It's not the only thing, but you want to have, to use an FPGA and good efficiency from it, you don't want to be doing everything with like a generic soft processor. You want to be using some of the more customized hardware-centric solutions for the heavy lifting, but you can combine those with easier to program solutions, things that are better at control flow, like soft processors, for simpler control, like finite state machines that are controlling a bunch of hardware units. And a generally good rule of thumb is just whatever model is simplest that can actually describe your computation is probably a good one to start with, because the simpler models tend to be more efficient. They're kind of stripped down. They guide you to build only what you need. So if you start with simple, probably makes it easier to get your system going, and also more efficient because you're not just adding in a lot of extra features that may not be useful. So any questions on that? If not, I'm going to go through a few slides on how this can turn into the compute model you choose can actually guide you towards useful tools. So there is a linkage between the way you think about your hardware and how you might choose, what CAD tools you might choose to implement it. So let me pause there for a second and just see if there are any questions. Okay, so I'm going to take that as a no. Okay, so last thing I want to talk about today is, I guess, just exactly what I just said. How does this link into the design tools you might choose to use? So you can write anything in hardware description language. So if when you're writing general hardware, you're mixing all sorts of compute models, etc., you can always write it in HDL. Now you can also go one level above hardware description languages to what's called high-level synthesis. And high-level synthesis tools go from usually a C-like language, doesn't have to be C-like, but C-like is the most common one, to hardware blocks. So their output is normally HDL. So they basically go from a higher level description to HDL. The key distinction is that HDL has clocks and high-level synthesis does not have clocks, okay? So high-level, because HDL doesn't describe every detail of your hardware either. We use synthesis to map the HDL into the chip, but it does describe the cycle-by-cycle behavior of exactly how you broke down the computation. And high-level synthesis doesn't. It describes the computation, but it doesn't tell you where the clocks are. So that's the additional step. Out of that comes Verilog or VHDL that can go through the rest of the CAD flow. High-level synthesis generally gets, compared to a very skilled HDL developer, usually it doesn't achieve as high a result quality, but it is getting better. Another interesting thing about high-level synthesis is generally to get good results from it, you need to still be thinking about the hardware that will be generated. So it doesn't mean you can just go write any C you want and it turns it into efficient hardware. You're thinking of a compute model, you're thinking of what hardware that will turn into, but it can allow you to be more efficient in doing that by taking away some of the details about saying, you know, exactly what are all the clocks and some more details of the hardware. But you have to be thinking about what the hardware is going to look like, usually. I mean, I guess I can't say that always, but usually that's how you get the best results with high-level synthesis. Okay, so let's say that you've decided that your computation fits a soft processor well. Well, then you can write it in C. And you can develop coprocessors for it, either in high-level synthesis or in a hardware description language like System Verilog. Streaming data flow, you can do in a hardware description language, and that's common, but you also have some domain-specific higher-level synthesis tools. So these tend to be, there are some special high-level synthesis tools that don't try to solve all problems, but they're very efficient for certain problems. So I guess I've told you some different tools here, and they're not all HDL, but HDL is like the FPGA assembly code. You can write it by hand, and unlike assembly code for processors, it is still commonly written by hand. I should go look up stats on this, but my belief, based on my experience, is that the majority of FPGA design is actually done in HDL. High-level synthesis is certainly not uncommon now. It is also used quite a bit, but more designs are actually done in HDL than in other languages. And even if you write in a higher level language, like some high level synthesis tool, what comes out is HDL. So it's important to be able to understand it, read it. Okay, so high level synthesis. So I already talked about this a bit. So the input is some untimed algorithm description. You don't specify the clock cycles. There are lots of different variations, but the most common things are it's some variation on C with some extensions to better describe hardware. Those extensions are sometimes pragmas, which means they're things that are ignored if you compile it through a software compiler because you're just trying to simulate and see if it does the right thing. Sometimes there are additional language keywords and so The output is an HDL, so either Verilog or VHDL with clocks. Popular tools in this are both Xilinx and Intel have high-level synthesis tools that basically take C with some additional pragmas, and they make modules. So you wouldn't normally describe your, well, for those tools, you wouldn't describe your entire design in HLS or one HLS kernel. It makes a block. So that block is a module that you can instantiate in your design. Again, by instantiating it in a higher level HDL design or some other techniques that I'll talk about in a minute. There's another set of high-level synthesis tools, again from Intel and Xilinx, that target Opencl. So Opencl is essentially a competitor to CUDA. So CUDA is NVIDIA's data parallel programming language for their GPUs, and it's proprietary to NVIDIA. It only works on NVIDIA GPUs. Opencl is very similar. It describes things in the same C with data parallelism extensions, but it's not proprietary. It can be compiled for CPUs, for various GPUs, and for FPGAs. Now, what an FPGA compiler for this does is pretty different than what a GPU compiler does. But it basically, again, takes that untimed code. So this is now C with some extensions to express parallelism and to express whether you're using on-chip or off-chip memory and so on. So some data locality information. And it will make HDL, so a big Verilog output, that's your accelerator. And this is a pretty big accelerator. So usually this accelerator will fill most of your chip. And it also makes the host code. So the host code is the code on a CPU that will talk to your accelerator. And that's actually a nice benefit of this flow. So if you're building a system where you're doing some compute acceleration and you need a CPU that is that's supervising it, it can be a fair amount of low-level coding to make particularly an off-chip CPU. So a CPU that's a Xeon CPU in a server talk to your FPGA over something like PCI Express and send your accelerator commands. So what these tools do is they don't just help you make the accelerator by taking you above the HDL level. They also allow you to write in a standard way communication between the CPU and the accelerator. And they'll compile that down to the appropriate memory mapped instructions and PCIe transfers and everything. So they save you a lot of work there. Internally, these two tools, so Intel's Opencl tool and HLS tool, like a lot of their code is the same, right? They're actually, the actual algorithms to make efficient hardware is basically the same, and the same for Xilinx. So they actually build kind of 1.5 tools and package them up in 2 different ways. If you're trying to make a hardware module, you give us a smaller amount of C with some annotations, we'll make you a hardware module. If you're trying to make a big accelerator, you give us all the code and we'll make you that whole big hardware module. And as an additional value add, we'll also allow you to code at a higher level to talk to a CPU. Okay, so another useful programming model is built around Simulink. So FPGAs, as I said, are used a lot for signal processing. And I'm not a signal processing engineer, but a lot of signal processing engineers optimize their designs in Simulink, which is a package that's connected to MATLAB. Okay, so Simulink is able to describe streaming computations. It's basically a block diagram tool that, again, signal processing and communication engineers use a lot. So I'm showing on this piece of the figure a block diagram in Simulink. And so these are a bunch of filters and communication components that are together doing some signal processing. And both Intel and Xilinx have products that can take a Simulink block diagram and turn it into hardware, and actually turn it into quite efficient hardware. So The tools are called System Generator for Xilinx and DSP Builder for Intel. The way they work is basically the signal processing engineer chooses blocks that Intel or Xilinx have provided, and each of those blocks is not just a filter. It is a filter or some communication modulation scheme, etc. There are a whole bunch of different blocks you can put in. Each of those blocks has a parameterized hardware generator embedded in it. So you put the block in, you configure it, you run all your Simulink simulations to see if you're getting the bit error rate you want and so on. But when you're done, you can push a button and those parameterized hardware generators will actually go and build you the hardware. So that can be a really efficient way to work if you're trying to build a signal processing system. Okay, so these are some slides that I kept from my time at Altera, so courtesy of Altera for the next couple of slides. The details of this are not that important, but basically, this is a particular communication system. It's for wireless networking. It's using 2 antennas, and this is doing something called a digital up converter. Okay, and I'm not the right person to tell you all the details of exactly why do I want to do the digital up conversion, but that's not my point here. Basically, what goes into this system are streams of data. So we talked about how streaming hardware is a nice fit to signal processing. So this tool allows you to express that pretty naturally. So you put down these various block diagram components. So here we have a FIR filter, and it's got multiple channels coming in. There's some scaling. There's an interpolation filter, so that's one where we're going to get more data coming out than came in. Some more scaling, some more interpolation and filtering, etc. So the designer basically builds his or her block diagram. And then they say how fast they'd like it to run. I would like the chip to run at a certain frequency. And they basically say generate hardware. So this is a nice one where the FPGA is kind of hidden from the signal processing engineer. Once they've got their system specified, if the compiler does well enough, they're kind of done. It's just going to go in the chip. Okay, so how does it work? So if Intel DSP Builder is the one that I'm more familiar with, but I believe the Xilinx system generator uses very similar techniques. So the programming model is streaming based on plot, and the input is with block diagrams. So the compute model is synchronous data flow, so one of the first ones we studied. It has valid data bits. So these signal processing systems, we saw there was an interpolating filter there, so it produces more output than input. So the data rate's not the same through the whole system, so we have to have valid bits to say when we have valid data. And that gives us the streaming style of decentralized control, or what's sometimes called data flow control. This tool does use back pressure and buffering where it needs to, but it's able to avoid using those most of the time. So it doesn't put a lot of buffering in, a lot of FIFOs in. It doesn't, and it'll have many modules where it can guarantee that the downstream module can always keep up with the upstream modules, and in that case, it doesn't even generate back pressure signals. So it basically uses the simplest streaming model that it can for each part of the design. The data path, to deal with the fact that different parts of the system may have different bandwidths because we have interpolation and decimation filters and so on, it doesn't actually change the clock frequency, it changes the data path width. So if you have more data, the data path gets wider to provide more bandwidth, more data. The clock frequency is a constraint. So it basically keeps pipelining your design, because these are feed-forward designs that can be deeply pipelined using the techniques we talked about, and it'll retime it, moving the registers to where it thinks are the right spots, until everything hits that frequency. So you just say, what is the frequency you want? And it just keeps, if you specify something beyond its capabilities, then it will fail. So it uses a latency tolerant design style to allow really deep pipelining. In Stratix 4, which is the generation where I had data on this, it could achieve 400 megahertz on complex designs that filled big chips, which is beyond what most human designers could do. So if we move this to Stratix 10, this 400 would be more like on the order of 800 or so. So only really excellent human designers could achieve these kind of frequencies. So it did get very good results and does get very good results. This tool is interesting because they actually built it two different ways. The first way they built it did not do this trick of keeping the clock frequency the same and just widening and narrowing the data path to get more data. The first version that Altera built actually did have different operations at different frequencies. That's how they made sure that the data rates all matched. And it wasn't as efficient. You needed clock domain crossing circuitry that added latency and complexity and so on. So it did turn out that it was more efficient to do things this way. Try to keep everything on the same clock domain, use valid bits, and just widen and narrow the data path. Let's see. All the IP cores that are used in this DSP builder tool are built to allow time domain multiplexing. So they have data, which is typically wide, maybe you have 128 bits of data, a valid bit to say if it's valid or not, and then a channel number. And the channel number allows you to do, the IP core can keep track of which channel is this, so it can do time domain multiplexing. But the IP cores had to be built with that feature. If you didn't have this channel being passed all the way through the streaming hardware block, you wouldn't be able to time domain multiplex it. Yeah, so I already mentioned this, and it commonly outperforms hand-coded HDL. And Xilinx has a tool called System Generator, which Chapter 8 of the Reconfigurable Computing book describes. So if you're interested in this kind of tool, I'd recommend you go and read that chapter for more information. Okay, so a few other tools that can be helpful. So that was about for feed-forward signal processing designs, and you want to do them in streaming hardware, those DSP builder tools are a great fit. Another important class of tools are software plus coprocessor tools. So I want to make an augmented processor. So, one way you can do this is you write the software code using just a regular software compiler, and you build the accelerators in HDL. So you go right into System Verilog or VHDL, or you might get them out of a library. And then you integrate them into the processor by writing those buses, those Axie or Avalon, or even your own bus in HDL. But this step of like connecting everything in buses by writing them in HDL, you can do it. You can read the bus protocol description. You can write HDL to implement it, but it's a lot of kind of plumbing that's a bit repetitive and people would rather not do. So for this style of design, it's more common to use a system integration tool that automatically creates the buses and the arbitration logic, et cetera, to say, maybe the coprocessor is using the bus right now, so the processor can't use it, and so on. So Intel has a tool called Platform Designer, and Xilinx has a tool called Vivado IP Integrator. What those tools do is take blocks of hardware, so IP cores, and they build buses automatically in between them according to your specifications. You can say who's a master and who's a slave on the bus and how wide you want the bus to be, and they'll build them. You don't have to write any RTL. And the number one use of those tools, but not the only one, is to build processors plus their peripherals. Xilinx has a tool that goes a little farther, which is kind of interesting. So their SD-SoC tool allows you to develop a C or C++ application. So you just write software, you compile it, you run it, you profile it, and that allows you to identify the hotspots in the software. And then you can mark the hotspot functions to be hardware accelerated. So you're working off one software code base. They invoke high-level synthesis to take that C or C++ and turn it into a hardware module. Now that C or C++, it doesn't handle all C or C++, so it's a subset. So you have to make sure those functions are written in that subset of the language. You might have to add some pragmas. But it allows you from that one interface to say, put this into hardware. And it'll run that hardware as basically a separate thread. Your software can now talk to it over a bus. So it can poll, are you done? It can choose to lock. You can synchronize with it using standard software constructs, which are actually being mapped to transactions over a bus. And those buses are automatically generated. So they're built with that IP integrator that I just mentioned, but instead of you saying, I want to make this hardware unit and this soft processor, you actually started from just one software specification and you marked certain key functions as I want this hardware accelerated. The HLS tool made the hardware, the integrator made the buses, and you just have to write the software to kind of synchronize everything. So this is an interesting and fast flow to help make it easier to make a custom coprocessor. And that's all I have to say about programming tools. So there are a bunch of different high-level programming tools. They all stack on top of HDL. It's in my opinion, it's difficult to do FPGA design without knowing HDL, but you can take significant parts of your system and try to hoist it to the level above to a tool that will generate the HDL for you. So it's useful to be aware of those tools. So that's all I have for today. I only finished 1 minute early, so sorry, I got pretty close to the end. If there are any questions, I'll hang around. And otherwise, good luck with assignment 1.
Thank you, Professor.
Thanks.
Thank you.
Okay, thanks. I'm going to stop recording. I'll keep hanging on, but that'll be the end of the recording.